physicists.
So something with an energy much larger than its mass.
Just to understand the historical context, so the monopole problem was a big deal because people just really believed in SU5 gut theories, or was it that
Yeah.
two different models also?
No, people thought they were about to win Nobel Prizes for them.
Okay.
Yeah. No, they were. This was absolutely. So my perception. So I was a grad student in these times, and my perception was like they'd just worked out the electroweak. Like these were people who, you choose a symmetry group, you choose representations, and you win a Nobel Prize. That was the mindset of the particle theorists at the time, and it already happened for electroweak, and so it was about time to happen with grand unification, and then Preskill comes along and just shatters it all, just like that, and it was pretty interesting dynamics. Yeah. So. Okay, there's equations showing the same thing I just showed you in the picture. Another thing that's a little bit more of a loose thing is you can work out, so in the standard Big Bang you start with a singularity, and going out there's a horizon. So a given region takes time to come into causal contact with another region, and if you can parse that different ways, but in these conversations we're used to talking about the gut epoch when the temperature is about 10 to the 16 GeV.
So time's upside down here, right?
And yeah, t equals 0 up here. And then it goes down. I don't know why. I flip flop on the direction of time in my slides. So yeah, here's the Big Bang. There's these different causally connected regions. We look back and we can see a variety of regions that have never been in causal contact. I probably should have, a more realistic thing to draw is we look at the microwave background, the edge of opaqueness, and we see, many orders of magnitude, 10 to the 12 or something, different causally disconnected regions there. And so you can just say, wow, the universe looks the same in all these different places and it's never been in causal contact. That's the narrative you get from the Big Bang. And again, whether you think that's a problem or not is another thing. So the flatness, homogeneity, and horizon features become problems if one feels one must explain the initial conditions. We've already had a little bit of this conversation. If you think the job of a physicist is to have good equations of motion and then work out what initial conditions you need to address the problem at hand and not worry about what, just think of the initial conditions as entirely in service to your solving of the equations, then you don't have to worry about that. None of these are problems. Although the monopole is more of a problem. If you believe the Big Bang and you want to grand unify or something like that, then that's more of a concrete problem. But these other things, like do you care about explaining initial conditions? And one of the reasons that this draws people in, so I like to give this analogy. So suppose you come into my office and there's a pencil just balanced on its point. And then you come back the next week and it's still there. And you come back the next week and it's still there. And at some point you say, geez, that's amazing. That pencil that's just balanced on its point week after week. What's going on? Now suppose I say, oh, yeah, it's pretty cool, but I don't have to explain it because it was like that when I moved into my office. That just doesn't seem right. It doesn't seem right. Whereas if the pencil's just laying on the floor, and you come back and say, oh, why is the pencil like that and not like that? That seems ridiculous because the state it seems like a more typical state. So that's what sucks people into worrying about the initial conditions for better or worse. And inflation does try to, the narrative that comes with cosmic inflation is definitely being sucked in by this puzzle. So now inflation basics. So we're back here with this Friedmann equation, and then we add another term. So we add another type of matter, which we call the inflaton. And back in the day, it was the grand unified theory Higgs field, but now it's kind of been liberated from that. It's roughly independent of the scale factor during the relevant period, and that causes expansion at a nearly exponential rate. Let's look a little more closely. And then right now, so one of the big questions is how you get this and how you get it into this equation of state to evolve in this way. But to separate out the loose stuff from the solid stuff,
So,
I'm just saying, just suppose.
by the scale factor, you say it's basically constant. It looks like it's similar to the dark energy.
It is. It's very similar. Yeah, it's,
But so why are they separate? How can you?
because they have very different sizes, and in fact, this has to change its evolution because this dominates the universe for a while at very high densities, and then it needs to stop dominating. If this just stuck around at high densities and didn't change, it would be worse than the monopole problem. It would. Let me just show you how. And you think of this. In a couple slides, I think I'll be able to tell you what I was just trying to say. So you think about the way people think about this typically is you think about a scalar field moving the potential, and you imagine somehow or other it becomes dominated by the homogeneous piece, and then it turns out that it's not that hard in various potentials to find regions where it does acquire that equation of state. And so here's now back to these pictures. So this is the dark energy. It's constant. You can also have dynamical pictures of dark energy. I've chosen a simple one. And it's just waiting around for the universe to catch up with it or catch down to it. And inflation is up here. And if this didn't ever change, it would just go straight out. And it would give a really whopping big contradiction with where we are today. So you have inflation. It's got to drop off in some way. And then you can say, oh, let's go ahead and have curvature of order the total density of the universe at some early time. And inflation sort of pushes the whole, waits patiently while the curvature dilutes, and then makes a standard Big Bang with very little curvature. So that's one of the things inflation can do for you. Same with monopoles. It can dilute the monopoles, and as long as you don't produce more of them after inflation, you've got a nice thing going on there. I happen to produce this plot by actually solving a scalar field with some friction in it, so you can actually do that. You can have a picture of what's actually happening, and you have some coupling to other matter. So it's rolling slowly, and then it starts oscillating in the potential, and this is converting energy into radiation, and so you can really think about this whole process pretty systematically. And this is a solution for field rolling in a quadratic potential. Now I want to tell you some more things about inflation. Yeah.
So why? I mean, you somehow set the scale of how long this inflation takes.
Yes.
What? And that's a parameter, I guess.
I'm going to tell you more about that in a little bit. But
Is that not fine tuning?
where does it I'm not going. So you're drawing me into the priors game, and I want to wait. So I don't want to answer that yet. I'm going to wallow around with that question soon enough.
All right.
I just want to go there. I want to go there step by step.
Okay. I was just going to make sure that you were. I mean, I don't see yet why it solves a fine tuning problem, but.
Yeah, I'm not really answering that yet. Wait, just wait. I don't want to.
Can I have a quick question? So in the previous plot, why the blue and the red lines, they only start at a certain point. So it seems like.
Whoops! Help! I'm going the wrong way. Oh, here we go. Yeah, I know. Like, what about this?
One previous. Before. Sorry. Before.
Just start over.
that's as far as I'm going to. Like, I'm running out of time, so I'm going to. I think the blue. Like, why don't I start the blue all the way back? Because all matter is relativistic, really, and then what happens is, as you cool off, some of the matter crosses mass thresholds and becomes non-relativistic. And I certainly not accurately modeled in that plot, but it was some attempt to sort of tip my hat to that feature. And let me. So I now want to tell you some more about inflation, and I want to go to a slightly different kind of plot, and I want to talk about the Hubble length. So instead of the Hubble parameter, I want to talk about the Hubble length, which is 1 over the Hubble parameter, and therefore it goes as 1 over the square root of the total of all these rows. And so when I give a longer version of this, I very carefully step you through first inverting it and then taking the square root. But the point is you get the flip of this Charlie noticed. You basically end up flipping this plot over. It's the same thing. So now I've gone to the trouble to say, well, this is just a formula for converting a density to a length. And I convert all the different densities to lengths, and then they show up. It really looks like I've just flipped the plot. And you should feel some security in that I've just reformulated it. It's all the same stuff in there, but now I'm going to take the total and ignore the details, and here we are. And this shows the entire history of the universe. So here's a period of inflation. There's the end of inflation. There's the end of reheating. So the end of inflation is when you no longer have that equation of state. But then it takes a while for the energy to get into the relativistic degrees of freedom. So that's the end of reheating.
Is that what reheating is?
Yeah.
What is it?
It's the coupling of energy out of the inflaton into the other degrees of freedom. And then there's electroweak scale, and maybe there's a phase transition there, and interesting things going on. Here's the formation of nuclei. I think I mentioned that sometime this week. That's a big deal because you can really model the formation of nuclei and do some tests with astronomical observations, and it appears that that's very consistent. That picture is very consistent with what you get from astronomical data. And then there's this point where the relativistic, non-relativistic matter change dominance, and if you look very carefully, you see a kink in this curve. You have to look very carefully because it's a log plot. And then eventually, well, here's today, and you see we're just at the point where the dark energy does dominate the density today. It's fortunately not totally dominating, but here we are.
Why is it leveling off like that?
Because that's the dark energy.
Oh.
So the dark energy in its simplest.
So it means the constant cosmic light.
Yeah.
Okay.
Yeah.
Where's the surface of loss scattering?
Yeah, why didn't I put that? It's somewhere here.
How can we say that stuff before that is then, how can we infer stuff?
So yeah, good question. So how can we infer, if that's as far as we can see, how do we have any idea what's going on here? And the answer is, and this is just our incredible good luck, is that what we believe to be true about the physics back here is actually pretty straightforward to solve. So you have a model of all this stuff, and you don't have to be a technical monstrosity to. You don't have to use a supercomputer to actually solve for important things that evolve there. So you make predictions. So what we believe we're seeing in the microwave background, the surface of loss scattering, is stuff that happened way back here, and we really do think we know how to model the evolution between there and there. For better or worse, you can be skeptical, but that seems to be working really, really well. I don't feel very skeptical about that. We're constantly improving. There's little details that people are improving the calculations, but that seems to be going pretty well.
So up to the inflation line, I guess, it's only that's just extrapolation of what we see today, and that's how far we can get.
Well, I'm going to tell you a little bit. Let's see if this is going to answer your question. I'm still getting used to this controller. So inflation tells us something about the fluctuations, as Adam already mentioned. It tells us something about the fluctuations we see today. And it's in particular, it has a simple relationship between, so we take it, if we can follow, so here's another kind of line on this plot. This is a co-moving scale that's scaling with the cosmic expansion. And it tells us that, roughly speaking, so there's actual equations people solve in detail, but roughly speaking, the solution to those equations tells you that the fluctuation in the density where this co-moving scale crosses the Hubble length here is given by a quantity that you can calculate down here. And that's true on a variety of different scales. So what we're really claiming is that we can calculate the inhomogeneities we see today based on an origin based on a calculation we're doing way back here. And this is where, as I've mentioned before, this is where a crucial ingredient is that we believe that the short wavelength quantum